Somewhere on Earth, for 4 billion years, a dull, reddish-brown rock sat buried in the dirt, completely unremarkable. Farmers stepped over it. Children kicked it aside. Builders occasionally used it to plug gaps in a wall. Nobody looked twice, because it looked exactly like what it appeared to be: compacted earth, heavy and lifeless, indistinguishable from the ground around it.
And hidden inside that rock was the material that would one day hold up the tallest buildings on Earth, haul freight trains across entire continents, form the hulls of ships crossing oceans, and eventually get hammered into the machines that would pull billions of people out of poverty. For almost the whole of human history, though, that rock just sat there, ignored.
The real question isn't simply how did we eventually discover iron? The deeper, far stranger question, the one that changes how you look at every bridge and skyscraper you've ever walked past, is how a person with no chemistry, no periodic table, no university, and no prior tradition to draw on could stare at a dull red stone and, through fire, accident, and what was probably thousands of failed attempts, pull a metal out of it that nothing in Stone Age technology had any business producing. And the answer to that question doesn't start underground at all. It starts in the sky. To understand how radical iron actually was, you first need to understand the world it replaced. For nearly 2 million years, human technology ran entirely on stone. Flint, obsidian, quartzite, chipped into edges sharp enough to butcher an animal, but fundamentally brittle. A stone axe could split wood, but one hard strike against bone and it shattered.
Stone tools also couldn't be reworked. Once the edge broke, the tool was finished for good. Then, roughly 5,000 years ago, something shifted. People across the Middle East and Eastern Mediterranean discovered how to smelt copper, itself a small miracle, realizing that certain greenish or blue tint rocks thrown into a sufficiently hot fire would surrender a soft, glowing liquid metal that hardened into whatever shape you chose.
Copper could be hammered into sheets, cast in clay molds, sharpened and resharpened. But pure copper is soft. A copper blade bends against anything tough rather than cutting through it. Then came a second discovery. Mix copper with tin in roughly a 9-to-1 ratio and you get something far harder and tougher than either metal alone, swelling into triumphant white vine enochics as the sword fully emerges. Bronze. For nearly 2,000 years, bronze was the defining material of civilization. Bronze swords, bronze plows, bronze chisels, the first cities, the first writing, the first empires. All of it powered by an alloy that needed 2 separate ingredients to exist. And that dependency was the problem. Copper was reasonably common, but tin absolutely was not. Its deposits sit scattered across a tiny handful of locations on Earth, parts of what's now England, pockets of Central Europe, corners of Central Asia. For civilizations in Egypt, Mesopotamia, and the Aegean, getting tin meant organizing trade networks stretching across thousands of miles of land and sea, but turning Thasida's trade networks. Ships hauling tin engroots down from Cornwall through the Mediterranean. Overland caravans dragging it from mines in Afghanistan toward the cities of the Near East. These supply chains were fragile. A single war, a broken trade agreement, or a sunken merchant fleet could leave an entire civilization suddenly unable to make its single most important tool. Egypt depended on that trade. The Hittite Empire depended on it. The Mycenaean palaces depended on it. And the whole time, sitting in the ground beneath every single one of their feet was the exact element that would eventually solve the problem completely. They simply had no way of knowing it. Iron is the fourth most abundant element in Earth's crust, making up more than 5% of everything beneath the ground we walk on. Mountains are laced with it. River sediment carries it. The reddish tint in clay soil across much of the world comes directly from iron oxide, rust mixed straight into the dirt. There is almost nowhere on the planet's surface where iron ore isn't sitting within reasonable reach. And yet, for thousands of years, people who had already mastered bronze, built pyramids, written literature, and drafted sophisticated legal codes couldn't do a single useful iron. A single useful thing with it. The reason is deceptively simple. Iron almost never occurs naturally as a metal. Unlike gold, which turns up as shining nuggets in riverbeds, or copper, which sometimes shows up as raw reddish chunks embedded in rock. Iron is almost never found in metallic form anywhere on Earth's surface, because chemically, iron has an extremely strong attraction to oxygen. Given any exposure to air and water over geological time, metallic iron converts to iron oxide, rust. Every scrap of naturally occurring metallic iron that ever existed on the surface has long since been chemically transformed into dull reddish stone. What ancient people saw when they looked at iron ore wasn't a hidden metal waiting to be freed. They saw red rock, brown rock, heavy rock that looked exactly like rock. It was rock. There was exactly one exception. It came from space. Nickel-iron meteorites. Fragments of the metallic cores of shattered asteroids. When a fragment survives the fall, lands intact, of native metallic iron, already in pure, usable form, alloyed with a small percentage of nickel. These objects were genuinely bizarre things to stumble across. They're far denser than ordinary stone. They're magnetic, visibly off dancing and convergings. Struck with a rock hammer, they don't chip or shatter. They dent. Cut or polished, they gleam like metal. Everything about them is wrong for a rock. And ancient people who found them recognized instantly they'd encountered something categorically different from anything else on Earth. They were right. In ancient Egypt, iron was given a hieroglyphic name that translates directly to metal from heaven, or stone of heaven. Not pathetic flourish, but a literal description, since the only iron Egyptian scribes had ever encountered had genuinely fallen from the sky. Ancient Sumerian texts used a time for iron combining the signs of sky and external, moon from beyond. Hittite ritual texts described it as the black iron of the sky. Across cultures separated by thousands of miles, with no contact between them, the exact same conclusion emerged independently. This material was celestial, and because it came from beyond the sky, it was treated with the reverence that implied. The earliest known iron objects in the archaeological record predate what historians call the Iron Age by more than 1,500 years. And none of them came from ore pulled out of the ground. They were hammered straight from meteorite fragments. In pre-Hellenistic Egyptian cemetery burials dating to around 3200 BCE, archaeologists recovered 9 small tube-shaped beads. Modern chemical analysis found extremely high nickel concentrations in them, an unmistakable signature of meteoritic origin. These beads had been hammered out of a chunk of iron that had literally fallen from space. In the tomb of Tutankhamun, buried around 1300 BCE, archaeologists found a dagger with an iron blade that sparked decades of scholarly debate. Finally settled by X-ray fluency testing, the blade contained nearly 11% nickel and trace cobalt, a composition matching a known meteorite recovered near the Egyptian coast. The king of Egypt was buried with a blade forged from a rock that fell out of the sky. During the Bronze Age, this kind of iron was rarer than gold. An ancient Assyrian trade records from Attila show iron commanding prices up to 40 times that of silver by weight. Iron rings and objects turn up in palace inventories right alongside jewelry, exchanged as diplomatic gifts between kings, symbols of extraordinary status, in an age when bronze itself was already the metal of power, which reframes the whole story. Long before any human figured out how to pull iron from the ground, iron was already known, touched, shaped, and treasured. It just came from the sky. Ore iron, the iron that would eventually remake the entire world, needed something else entirely to unlock it. It needed a kind of fire that didn't exist yet. Here's the thermologic wall that delayed the Iron Age by thousands of years. Copper melts at 1085 Celsius. Bronze melts even lower, around 950 Celsius, since alloying with tin drops the melting point further. Bronze Age kilns and furnaces were built specifically to hit these temperatures, and pottery kilns of the era regularly reached between 1000 and 1150 Celsius, plenty hot enough to liquefy copper and bronze and pour them into molds. Pure iron melts at 1538 Celsius. That roughly 400-degree gap between what Bronze Age furnaces could achieve and what iron actually required, it was a minor engineering hurdle. It was a completely different category of problem. No matter how expertly operated, a furnace built to smelt copper and cast bronze was physically incapable of liquefying iron ore. There's archaeological evidence early metalworkers actually tried placing iron-rich rocks into copper-selving furnaces, waiting for liquid metal to pool at the bottom. Nothing happened. The iron didn't melt, didn't flow, just sat there, red-hot and stubbornly solid, offering nothing useful. Every logical inference available at the time said iron was simply a useless rock. Turning it into metal required a completely different method of extraction, one that didn't rely on melting at all, and nobody had discovered it yet. The path there wasn't one single breakthrough. It was a slow accumulation of furnace knowledge across generations of people who had no idea they were building toward anything in particular. The first real improvement was charcoal. At some point, metalworkers stopped burning raw wood and switched to charcoal. Wood slowly heated with almost no oxygen to drive off water and volatile gases, leaving behind something close to pure carbon.
It burns hotter, more consistently, with less smoke, and raises a furnace thermal ceiling significantly. The second improvement was enclosure. Open hearths gave way to stone and clay-walled structures, tall enough to create a chimney effect, a rising column of hot gas that pulls fresh air in from below. And the taller the shaft, the stronger the draft. And the stronger the draft, the more oxygen reaches the burning charcoal. And more oxygen means higher temperatures.
Nobody designed furnaces with this specific logic in mind at the time. The logic came later from modern archaeology and experimentation. Ancient builders who made their furnaces taller simply noticed, imperatively, that the fire burned better. The third and probably most consequential improvement was the bellows. Leather bellows pumping air directly into the base of a furnace through clay nozzles, forcing airflow in a way natural draft alone never could, pushing sustained furnace temperatures as high as 1200 Celsius or beyond.
None of these three innovations were developed with iron in mind at all. Fitz is not for iron. Bronze smelters simply wanted hotter, more efficient furnace to smelt copper, fire pottery more evenly, and waste less fuel. They were solving immediate, practical Bronze Age problems. But the cumulative result, refined across centuries, was a furnace capable of something its own builders never intended.
What happened next almost certainly wasn't witnessed by any single person in any single moment. The best reconstruction, built from archaeological evidence and modern experimental metallurgy, goes something like this. A copper smelter running a charcoal-fueled, bellers-driven shaft furnace added iron earring rock to the mix, possibly on purpose, since iron-rich rock was sometimes used as a flux to help separate impurities out of copper oak, or possibly because the furnace walls themselves happened to be lined with iron-rich clay and stone. Either way, iron ore ended up inside a furnace burning somewhere between 1000 and 1200 Celsius. At that temperature, iron oil doesn't melt, but something else happens. Charcoal burning in a partially enclosed space doesn't combust completely. With limited oxygen, the carbon produces carbon monoxide instead of carbon dioxide, and carbon monoxide is chemically aggressive towards oxygen-bearing compounds. As it rises through the furnace shaft, it encounters the iron oxide in the ore and strips the oxygen atoms straight off the iron atoms. No melting required. Just a chemical reduction happening entirely in the solid state, transforming an oxide compound directly into metallic iron. Not liquid metal. What forms as a result isn't a pool of liquid metal at the bottom. It's a spongy, porous mass of metallic iron particles fused together, still riddled with glassy salt, roughly holding the shape of the original ore. This mass is called a bloom. Whoever first broke open the bottom of that furnace, expecting to find copper, or slag, or nothing useful at all, instead found something that had never existed before. Dark, porous, not remotely shiny, looking almost nothing like metal. But struck with a hammer while still hot, it didn't chip or shattered. It bent. It defoamed. It was metal. Something entirely new had just entered the world. What's genuinely striking, studying how ancient ironworkers actually operated, is how precisely they learned to control this process purely through observation, with zero theoretical framework to explain any of it. Smelters learned to identify high-quality iron ore not through chemical analysis, but by weight, color, and where in the landscape it was found. Dense, dark rock from specific geological formations reliably produced better blooms than light, reddish, earthy material.
Inside the furnace, experienced operators read the flame itself, judging temperature by the color visible at the top of the shaft. Bright yellow-white meant good reduction conditions. Dull red meant insufficient heat. They developed a feel for the exact bellows rhythm that produced a good run, learned to judge from the viscosity of the liquid slag draining out the tap hole whether the furnace chemistry was on track.
The ratio of charcoal to ore, the height of the charge, the pumping rhythm of the bellows, exactly when to stop and extract the bloom, all of it learned empirically, generation after generation, and passed down purely through apprenticeship. No written metallurgical texts existed, no formulas, just observation, memory, and the oral tradition of the workshop. The ancient bloomery worker had no concept of carbon dioxide reduction kinetics, iron oxide phase transitions, or solid-state diffusion thermodynamics, but they had mapped the entire input-output relationship of the process with extraordinary precision. They knew exactly what to feed the fire and what would come out. They simply had no idea why any of it actually worked. The technology that became the world standard for iron production for thousands of years was the bloomery furnace. A vertical shaft, typically 1 to 2 meters tall, built from fired clay, fieldstone, and straw binders. Charged from the top, with alternating layers of charcoal and clay and crushed ore. Alternating layers, clay, stone, charcoal, and cementing knit.
Near the base, one or more clay nozzles connected to leather bonges forced air into the glowing fuel fed, and at the very bottom, a tap hole let liquid slag drain out, or the wall could be broken open after each run to extract the bloom. Hotter zones became molten zones. For stape iron in slag, insecting oil has dimmet reduction intensifying. No melting, there is slaggus, iron production, like tamed Sogol Phyles chemical cruisin redestus.
The metallic particles formed near the hottest zone, scenting together under their own weight and the furnace heat into a spongy, consolidated mass, while silica impurities reacted with some of the remaining iron oxide to form a liquid slag that drained away. A single bloomery run could run several hours and yield anywhere from a few kilograms to tens of kilograms, depending on furnace size and ore quality. And when the bloom finally came out, the real work was just beginning. A raw iron bloom isn't usable metal. It's porous, structurally weak, riddled with trapped slag. Left as it is, it would simply crack apart. Turning it into something useful was the blacksmith's job, and it was brutal work. While the bloom was still glowing at near white heat, above 1000 Celsius, it was transferred to a stone anvil and beaten with heavy hammers, blows that squeezed slag out through the surface as the metal compressed, collapsing internal voids and bringing the iron particles into direct contact. At those temperatures, the touching particles physically fused together at the atomic level, a process called solid-state diffusion welding, with no melting involved at all. Repeated hammering broke up the coarse internal crystal structure, refining it into a stronger, more organized grain. The result of all that sustained, punishing labor was wrought iron, a low-carbon metal with excellent tensile strength and remarkable toughness. It could bend severely without snapping, absorb shock, and be reheated and reshaped repeatedly. It could hold an edge, though not quite as well as the best bronze, but it no longer required tin from the other side of the known world. Still, the true potential of iron remained hidden. The next breakthrough, the one that finally made iron undisputably superior to bronze, came from yet another accident buried inside the ordinary daily practice of the forge. Wrought iron has a real problem. It's tough, but soft. An edge subjected to heavy use, cutting bone, chopping hardwood, clashing against another blade, deforms and dulls quickly. Well-hardened bronze holds an edge better. The missing ingredient bridging that gap is carbon, and ancient blacksmiths had absolutely no idea it existed. What they did know, through accumulated hands-on experience, was that iron left in extended contact with burning charcoal behaved differently than iron processed quickly. It grew harder, stiffer. A blade left sitting in a hot charcoal tithe for hours, heated and reheated, came out changed. The actual reason, unknown for thousands of years, is this. Heated above roughly 900 Celsius, iron undergoes a shift in its internal crystal structure, entering a state called austenum, where the lattice develops gaps between atoms exactly the right size to accommodate carbon. As the hot iron sits surrounded by burning charcoal, carbon atoms migrate straight from the charcoal surface into the metal, filling those gaps. The iron absorbs carbon directly. Even a tiny amount, under 1% by weight, changes iron's mechanical properties dramatically.
With enough carbon absorbed, iron becomes steel, and steel quenched rapidly by heating to the right temperature and plunging into cold water, locks its carbon-enriched structure into a form called martensine, extraordinarily hard enough to cut and scratch bronze with ease. The blacksmiths who first produced this harder metal never planned it.
They simply noticed that blades made from certain sections of a bloom or treated in specific ways during forging came out harder than others, and developed reliable practices. Longer heating times, specific quenching routines, particular fuel contact techniques that consistently reproduce the result. They gave it different names in different languages. They knew exactly how to make it. They had no framework whatsoever for understanding that the real cause was a chemical element called carbon migrating into iron's atomic ladder. For several centuries after ironworking developed in Antillasia and the Laurite, roughly between 1500 and 1200 BCE, it remained a secondary technology. Bronze still dominated the infrastructure, the skill base, the trade networks, and the cultural prestige of the age. Then, around 1200 BCE, something catastrophic happened. In the span of roughly 50 years, nearly every major civilization in the Eastern Mediterranean either collapsed or was severely disrupted. The Mycenaean palace system of Greece disintegrated. The Hittian Empire, one of the dominant powers of the ancient Near East, ceased to exist. Coastal cities from the Levant to Cyprus burned. Egyptian records describe invasions by groups referred to only as the Sea Peoples. The interconnected palace economy that had sustained those long, fragile tin trade routes collapsed with it. Historians still debate the exact causes of the Late Bronze Age collapse. Climate stress, internal social pressure, mass migration, earthquakes, and cascading trade disruption are all implicated. What isn't debated is the outcome. The tin supply collapsed, bronze production crashed across the region, and the material that had powered civilization for 2,000 years suddenly became difficult and expensive to obtain. Metalworkers facing that shortage looked at what was actually available locally, and iron ore was everywhere. The bloomery furnaces they already knew how to build could produce useful metal from local rock with zero imports required, got violently accelerated by sheer necessity. Civilizations with a genuine choice between bronze and iron had mostly stuck with bronze. Civilizations facing a tin crisis chose survival instead. What emerged from that crisis was a world increasingly dominated by iron. And over the following centuries, as blacksmiths across the Mediterranean and Near East refined their carbureting and quenching techniques, iron proved not just an adequate substitute for bronze, but genuinely superior to it. That comparison isn't simple, though, and the historical record makes clear that the transition took real time, precisely because unrefined iron genuinely wasn't as good as well-made bronze at first. Raw, uncarbonized wart iron, measured on standard hardness tests, sits significantly below a properly work-hardened bronze blade. Early iron tools really did bend more easily in use. That's exactly why the Iron Age didn't begin the instant bloomery smelting was discovered. The techniques for turning iron into something genuinely better than bronze took centuries to develop. But properly carbonized, quenched, and tempered steel belonged to a completely different category. A well heat-treated steel blade achieves 2 to 3 times the hardness of the best bronze, holds an edge longer, resists fracture better, and can be made lighter for equivalent strength. Then there was the economics. Bronze needed both copper and tin demanded trade routes spanning continents, which made bronze expensive enough that armor, weapons, and quality agricultural toys stayed largely limited to military elites and wealthy landowners. No society could equip a mass army in bronze. Iron ore, by contrast, existed almost everywhere, and charcoal could be produced from forest in nearly any region on Earth. A single village with a bloomery furnace and a blacksmith could produce its own iron entirely without imports, and as technique improved, the cost of iron tools kept dropping. A peasant farmer could own an iron plow. A common soldier could carry an iron spear. Metalworking knowledge that had once been concentrated inside palace workshops, Trebant's clips, began spreading into ordinary communities. A genuine democratization of metal that reshaped agriculture, warfare, and the distribution of productive capacity across entire societies. When iron got cheap enough for an ordinary farmer to own iron-tipped tools, land productivity jumped dramatically. When armies could be equipped with iron at mass scale, the nature of military conflict itself shifted. It's worth pausing on the village blacksmith who appears across so many cultures throughout history, because in the ancient world, that figure carried something close to magical significance. To anyone without chemical knowledge, the blacksmith's work was genuinely inexplicable. They took dull reddish rock, put it into fire, worked the flame with bellows, pulled out a shapeless spongy mass, heated again, hammered it for hours, and produced a blade, a plow tip, or an axe head harder and sharper than anything that had existed before. Nothing about the rock going in prepared you for the metal coming out. The entire transformation happened hidden inside a fire. Across world cultures, entirely independently, ironworking became linked to divine power. In Greek and Roman tradition, Hephaestus and Vulcan, the divinic blacksmiths who forged weapons for the gods, were figures of both awe and unease, powerful enough to require lemonness or isolation as a kind of cosmic balancing act. In West African and Urardi tradition, Ongo is the deity of iron, warfare, and metalworking. Revered as patron of blacksmiths and hunters alike, Celtic mythology's god Go knew the power to forge weapons that never missed their mark. In Norse, the dwarfen smithens who forged the weapons of the Airist were considered the most technically skilled beings in existence.
None of this is coincidence. It reflects a strikingly consistent response across unconnected cultures to the exact same phenomenon. A person capable of turning rock into metal possessed knowledge that felt genuinely beyond ordinary human comprehension. The eye's real alchemy, his certist as blacksmith, and a textury beyond ordinary comprehension. There's ancient magic. Diljovisurge et tite of blackamy gruler jansicist outdacient perceptivated. Multiple civilizations, largely independently, developed distinct ironworking traditions. Metallurgists pushed furnace technology, reaching temperatures hot enough to fully melt iron and produce true liquid metal. Fully melted iron absorbs far more carbon, producing cast iron, brittle but extremely hard, and powerable into molds for complex shapes.
By 31 CC, a Chinese official named Du Shi was using water wheel power to drive blast furnace bellows, mechanizing iron production roughly 12 centuries before Western Europe would manage the same feat. In India, metallurgists developed the technique behind what became known as Watt steel. Sealing Vort iron with organic carbon sources inside clay crystals produce high carbide inks that, forged carefully, develop distinctive microscopic carbide banding. Blades made from this material, exported across the Indian Ocean and traded through the Middle East and eventually Europe as Damascus steel, were famous for combining extraordinary hardness with real flexibility, and the technique stayed so tightly guarded that European metallurgists couldn't reproduce it until the 19th century. Across sub-Saharan Africa, particularly in the Great Lakes region and West Africa, independent bloomery tateries developed before the Common Era, with some African smelters engineering tall, natural draft furnaces that preheated incoming air before it reached the charcoal bed, achieving efficiencies without mechanical bellows at all, a thermonomical design principle that wasn't formally articulated in European engineering until centuries later. Iron, in other words, wasn't one story. It was many separate stories, arriving at closely related conclusions through completely different routes. The broad spread of iron tools across farming cultures fundamentally reshaped what agriculture could achieve. The heavy iron moldboard plow was a qualitative leap over anything made of wood tipped with bronze or stone. Wooden scratch plows could manage the light soils of the Mediterranean, but the dense clay soils of northern Europe and much of Asia resisted them entirely. An iron moldboard plow could cut deep into heavy soil, turn it over completely, and bury surface vegetation, dramatically improving fertility and weed control, and regions that had never supported large-scale grain farming suddenly became productive agricultural zones. Iron axes and addos made forest clearance practical at scales previously unimaginable, converting woodland into farmland. Iron sickles cut grain faster and cleaner than stone or bronze ever could. Iron chisels and saws made precision carpentry and stonework by ordinary craftsmen, not just those with access to costly bronze tools. Iron nails made structural carpentry stronger and faster. Iron fittings and chains extended what wheeled transport could haul and how far. Cast iron cookware, produced in China quite early in the iron tradition, enabled cooking methods ceramics simply couldn't manage. Every profession the material touched found itself able to do more, faster, with less. Not overnight, the transition was genuinely slow, but cumulatively, across centuries, it was total. A world built around stone and bronze quietly became a world built around iron. The bloomery furnace, for all its ingenuity, had real limits. Each run produced a relatively small bloom. The process was labor-intensive and stop-ot, and scaling up meant building more furnaces and hiring more workers, rather than reinventing the process itself. The blast furnace, which emerged separately in Europe and China across the medieval period, changed that entirely. A continuously operating version of the same basic bloomery concept, but large and hot enough to fully melt the iron, producing large volumes of liquid pig iron that could simply be tapped from the base. Chinese furnaces achieved this by the early Common Era. European blast furnaces became widespread around the 13th and 14th centuries. Pig iron, though, carried too much carbon for most direct uses, hard but brittle, requiring further processing to vert back techniques like the puddling process Henry Cort developed in 1784, stirring molten pig iron in an oxidating atmosphere to burn off excess carbon. Then, in 1856, Henry Bessemer patented the converter that carries his name, a vessel that blasted cold air through molten pig iron, burning off carbon and silicon using nothing but the heat generated by the chemical reaction itself. Within minutes, tons of pig iron became structural steel, no additional fuel required. The Bessemer converter made mass-produced structural steel economically viable for the first time in history, and the skyscrapers defining modern cities, the railways connecting continents, the ships making daily global trade possible, all of it followed directly from that single innovation making large-scale steel cheap. In a very real sense, the Industrial Revolution was the moment the exact chemical process an anonymous bloomery operator had stumbled into thousands of years later finally got scaled up large enough to reshape the physical world. Same reaction, same chemistry, carbon monoxide stripping oxygen from iron oxide inside a hot enclosed furnace, just executed at a scale billions of times larger. One of the more unusual disciplines in modern archaeology is experimental metallurgy, researchers building replica bloomery furnaces from ancient materials and techniques specifically to understand exactly what ancient smelters were actually doing. These reconstructions aren't guesswork. They're built from precise measurements of surviving ancient furnace remains, chemical analysis of slag deposits revealing exactly what temperatures and ore concentrations were involved, and comparisons against ethnographic records of traditional ironworking communities that kept practicing bloomery smelting well into the 20th century. When archaeometallurgists run these replicas, packing them with charcoal and local iron ore, operating hand bellets for hours, eventually breaking the base open to recover the bloom, they consistently produce genuine metallic iron using nothing but ancient materials and methods. The process works exactly the way it must have worked thousands of years ago. This matters because it settles a question that once seemed genuinely uncertain. Could ancient people, with zero theoretical understanding of chemistry, actually have developed this technology on their own? The answer is unambiguably yes. Bloomery smelting doesn't require understanding chemistry at all. It requires observation, experimentation, and the accumulated practical knowledge that comes from generations of people repeating a process and paying close attention to what happens. Modern chemical analysis adds another layer to the story. Portable X-ray fluorescent testing, electron microscopy, and metagraphic analysis of polished cross-sections let scientists determine the exact carbon content of ancient steel, identify which ores were used, reconstruct the forging temperature of a specific blade, and even tell whether a tool was quenched in water or simply air-cooled. Ancient artifacts carry their own manufacturing history encoded directly into their microspector, fully readable with modern instruments. Several persistent myths about iron's discovery have been fairly clearly refuted by the archaeological record. The first is the Hittian monopoly theory. For much of the 20th century, historians suggested the Hittian Empire had discovered and jealously guarded iron smelting technology, releasing it to the world only once the empire collapsed around 1200 BCE, based on a handful of Sincarep texts describing iron as a closely held Hittian product. The archaeological evidence simply doesn't back this up. Iron smelting sites and artifacts appear at comparable dates across Anatolia, the Levith, Mesopotamia, and the Caucasus with no sign of any centralized monopoly. The Hittins used iron, they didn't own the technology. That myth mostly reflected how early 20th century historians expected technology to spread outward from a single origin point, rather than how it actually tends to develop, in parallel across multiple sites where similar conditions produce similar solutions independently. The second myth is the lone brilliant inventor. No single person discovered iron, and no single culture holds any kind of foundational claim on it. It emerged from thousands of small, individually unremarkable improvements, observed by people who had no idea their small tweaks would eventually accumulate into a revolution, passed down to apprentices who refined them slightly further, and spread by migration and trade to groups who adapted the technique to their own local conditions. The history of iron is, essentially, a history of unaccredited incremental progress. The third myth is that iron immediately replaced bronze simply because it was immediately superior. It wasn't, at least not in its raw, unrefined form. Wrought iron was genuinely softer than good bronze, and iron's real superiority only materialized once carbonation, quenching, and tempering techniques matured, a process that unfolded over centuries rather than within a single generation. The shift to iron wasn't a sudden revolution. It was a slow transformation that played out over hundreds of years, at different speeds in different places, as the full toolkit of iron metallurgy gradually came together. Stand in any modern city and look up. The frame of the building above you is steel. The beams holding up the floor beneath your feet are steel. The rebar buried inside the concrete foundation is steel. The bridge you crossed to get here, the train that carried you, the ship that hauled the goods sitting in the shops around you, all steel. The cars on the road, the cranes that raised the buildings, the pipes carrying your water, the cables carrying your electricity.
Steel and iron in every direction you look, and every single gram of it was once dull reddish ore, pulled straight out of the ground. Run through a furnace where carbon monoxide stripped the oxygen off iron oxide and left pure metallic iron behind. The scale differs by a factor of millions. The underlying reaction hasn't changed at all.
What began as an accidental encounter between iron-bearing rock and a charcoal fire inside a copper smelter's furnace, witnessed by someone who had no idea what they were actually looking at, became the material foundation of the entire modern world. And that connection isn't a metaphor, it's direct. Every generation of metallists since, from anonymous ancient bloomery operators all the way to Henry Bessemer and the engineers running today's electric arc recycling furnaces, has been working with the same material, the same underlying chemical principle, and essentially the same problem of how much carbon enters the iron, and what happens to it once it cools. The person who first pulled a bloom out of a hearth, hammered it, and realized it was metal, wasn't standing at the beginning of some separate, smaller story. They were standing at the very beginning of this one. The one still holding up the building you're probably sitting in right now.